really tempted to got this thing. I got a pair of bananas that have sharks for feet. I'm really tempted to wear them to school. They're really comfortable. Yeah, like super warm. But I just
say sharks for feet.
Sharks for feet.
I believe that's how it's actually. So I think
It's totally nostalgic.
I don't know. I always stress. I was stressed out.
Oh yeah.
That's still
Not as much as it used to be, like 75% of the women.
All right, I'm going to get started here. It's exactly 10:30, despite what the clock is telling us, because according to the clock, time has frozen. Which may or may not be a good thing, depending on a lot of factors. All right, so let's go ahead and get started. We are going to finish the binary search algorithm, the correct one today. We'll talk about the floor function a little bit. I'm going to point out where you can find the information. I'll let you guys read about it. And then we'll move on to subroutines today, which is a big, huge, important topic. And I have noticed that a lot of people have not read or clicked on the links on the website. It's probably okay up to this point, but when we get to subroutines, it's a kind of difficult kind of thing for at least to some people. So I think reading may be useful. Watching YouTube is definitely useful too. But the material that I have written, that is prepared, can also be helpful, depending on what kind of a learner you are. Some people are more visual, other people are more auditory or multimedia, and then some people are called what we call abstract learners, so they also learn in a different way. I took a screenshot of where we left off last time, so we can just use this as a starting point. But before I go, before I start with this, what I'll do is I'm going to go to the let's see here, latest news, which kind of talks about what is the floor function, because the floor function is mentioned in the homework assignment, but it was not mentioned in class. I was kind of assuming that people would read the notes, and so even after this, I was checking on Moodle and see how many people actually read the note, and not a whole lot. All right, so in here, there is in algorithm, the floor symbol is this part here, and if you just use your browser to look for floor, it kind of explains it right here. Okay, the floor of x is the largest integer that is less than or equal to x. Okay, another way, my favorite way of looking up stuff, when I don't know what it means, is Professor Google. So you just say floor function, and then you go to Wikipedia, and it has, wow, look at all this stuff here that explains what a floor function is. So there are resources, but it's explained here. I mean, this is really the most concise explanation of what is the floor of something. Yep.
Going back to that Wikipedia one, that's where I found it, but I wasn't clear on if B and E is equal to 1 and divided by 2, so it's going to give you 1/2, so the floor 1 or 0.
Well, what do you think? The floor of something is the largest integer that is less than or equal to the value. So what is the largest integer that is less than or equal to 0.5?
0.
There you go. It is 0. Because 1 is not less than or equal to 0.5, so it cannot be 1.
Right.
And it cannot be 0.5 itself, because 0.5 is not an integer. Yep.
So that way it differs from rounding.
It is not the same as rounding, correct.
Right, so 0.5 would be rounded up to 1,
correct.
But the floor is just kind of like more like a threshold kind of.
Yes, but it's also not the same as dropping the fractional part, because what is the floor of negative 0.5, right? Negative 0.5. What is the largest integer that is less than or equal to negative 0.5? It's not 0.
Negative 0.
It's negative 1, because it still has to be less than or equal to that value. 0 is not less than or equal to negative 0.5. Right? So that's why it's called the floor function and not, it's not called the integer function.
Right.
The integer function takes the integer part of a number and basically just ignores the fractional part.
Right.
This one takes a step, takes a step down to whatever integer is less than or equal to the number, to the value.
And what was the symbol? What was the symbol again that you highlighted earlier?
The symbol that we use here is, this is the mathematical floor function, which looks like a square bracket except it's missing the top.
Oh, okay.
So it looks like, the floor of something.
Okay.
All right. Okay, but the good thing is at least, people understand, hey, there's a floor function here. I better ask, about what it is. So that's good. It's better than, people looking at that symbol go like, whatever. I'm going to take a little guess here of what it is. So asking is good, but reading the notes is even better. All right, so we're going to finish the algorithm here, and the homework assignment is due on Thursday. And this is where we left off last time. I'm going to use mousepad to repeat at least this part, and then we'll continue with the algorithm. Oh, where's my mousepad? Under accessories, mousepad, there we go. All right, so I'm going to do a really quick job here and just retype it. Let V be the index of the first element that equals K. That may, okay. There we go. So we are keeping track of which part of an array may still contain, the value K. And we are, with each comparison, we are eliminating parts of an array so that we are only keeping track of which part can still contain that particular value. And B is the index of the first element that can potentially be of value K. And then the other variable E is the index of the last element that may equal K. In other words, we are basically keeping track of the beginning and the end of a certain range in the array that can still contain the value K. Yes?
Sorry, this may be silly, but this is all of this formula assumes that everything is ordered.
Yes.
Correct.
The array has to be sorted for binary search to apply. That is correct. Okay. So now we have the algorithm itself. It starts with loop because we know it is a loop. The first thing we do in the loop is to compute M in this case, which is the index of the element that we're comparing to. In this case, you can see that I do not have the floor function because the examples that have been given you, they're all powers of 2 minus 1, where it is guaranteed that b plus e divided by 2 is always a whole number. It's always an integer. Okay, but that can change because in the homework assignment, I artificially introduce a bug into it. So even if we start with bar a bar being a power of 2 minus 1, it will still end up with fractional numbers or halves. Okay, and then last time we realized that when the key that we are looking for is, okay, in this class we actually spell the name key. If the element that I have selected to compare to key is less than the key, we can do something. We can adjust one of those two, B or E, so that we can shrink the range in the array that can still contain the value K. Okay, we can limit and say, okay, we know that the value K can only exist between this element and this element in the array. So we're not quite sure which one we adjust yet, but we know we can adjust one of them. And then the same thing applies when a bracket m is greater than key, then we can adjust the other one. Okay. Last time, we stopped right there, because I did not have enough time to analyze and figure out, which one we should be adjusting. The exit condition is, the first one is simple. Okay. The exit condition, the first exit condition is a bracket m equals key, which means, hey, we just found it. Okay. Because as soon as you find one element in the entire array that equals the value that you're looking for, it's time to exit, okay? Because the question is not how many elements have the same value as key. The question is there at least one? So if you find one, you're good, it's time to exit. The other part, we still have not figured out yet, because we are basically saying once we confirm that all elements are eliminated, in other words, none can contain the value key, then we can also exit, because we know, the value does not exist in the array. So that's basically where we left off last time. Is this particular partial algorithm. What we'll do today is, one, we'll finish it, we'll trace it a few times, and then we're going to move on to subroutines. Are we doing okay so far? Any questions? Okay. All right. So what we need to do now is to say, okay, well, this is a good portion of the algorithm already. But if you look at how we use B and E, I haven't really talked about what value they should start with. Okay, and that seems kind of important, because the first thing we do in the loop is to say, oh, let's go ahead and use B and E to compute M. Okay, so we have to start with something. What do you think we should start with B and also E? What is the index of the first, before the first comparison in the array? What do you think is the index of the first element that may contain that value key? 0, okay? Very good. What about the index of the last element that may contain the value key? Go ahead.
Bar A bar minus 1.
Bar A bar minus 1 is the right answer, okay? Because that's the index of the last element of the entire array A. Okay? So we're doing okay so far at this point. Okay, so that takes care of the initialization. Now we have to look at this part here and say, but what if A bracket M is less than key? I'm thinking we need to adjust one of those two, B or E, so that in the next iteration, M is going to get a potentially different value. So which one do you think we should adjust, assuming the array is sorted in a non-decreasing order? Or, if you will, increasing order if duplicate values are not expected. We have to adjust B. Yep, that is correct. Because if A bracket M is less than key, that means A bracket M minus 1 is also less than key. It also means A bracket M minus 2 is less than key. In fact, everything before A bracket M, including A bracket M itself, they're all less than key. So we can move the index of the first element that may contain the value key to where? Now, in the homework assignment, I use M here, okay? And I told you that is incorrect. For those of you who just read the notes, okay, I just briefly displayed the correct algorithm. So how many people actually caught a glimpse of that and say, oh, so that's what it's supposed to be? I know M is not correct, because remember, B is the index of the first element that can still have the value key. How did we get into this branch here? What condition has to be true to get here? A bracket M is less than key, right? So that means M cannot be the index of the first element that can still have the value key. So what is the next one? Plus 1, right? M plus 1 is the next one. So that's why in this case, B has to be M plus 1 and not just M itself. Okay? So it is not the same as your homework assignment, because your homework assignment has an intentionally broken algorithm, because I want you guys to see what happens when we just miss a plus 1 and a minus 1. Okay? But this one is correct. Okay? We say, okay, we only know up to this point, it cannot be a value key, but the next one can be value key, okay? Now the other one, is probably pretty easy, because we either adjust B or E. In this case, if A bracket M is greater than key, it also means A bracket M plus 1 is greater than key, A bracket M plus 2 is greater than key, and so on. So everything starting with A bracket M and after that will be greater than key. How should I adjust the index of the last element that may have the value key? It's related to M. Go ahead. M minus 1, because that is the one right before the one that I just compared to and confirmed that it is not key. Okay, so that is the correct answer. All right, so we'll go ahead and say, okay, here's another revision. We just finish a very significant part of this algorithm, which is to determine how B and E are adjusted with each iteration. Okay, we still have two things to finish up, and one is particularly important, which is how do we know all elements are eliminated? In other words, we have just figure out that, hey, no element in the entire array may contain the value key. How can we get to that point? Okay, so if you think about this algorithm, unless A bracket M equals key, for each iteration, one of those two variables will get adjusted. Either B is adjusted or E is adjusted. Is that right?
Right.
Okay. Because if you look at the comparison, or if you look at the conditional statement, if key is greater than A bracket M, we adjust B. If A bracket M is greater than key, we adjust the other one, which is E. But every time we do an adjustment, B is guaranteed to become greater than what it was. And every time we adjust E, it is also guaranteed to be less than what it was before. So that means if you look at it visually, we start off B over here, we start off E down here. Every time we adjust, we're moving those two closer and closer, right? When they are the same, what does it mean? When B and E are exactly the same, well, let's think about it, okay? When B and E are the same, it means the index of the first element that can contain the value key is the same as the index of the last element that can contain the value key. That means we have one element left to compare. Okay? When they overlap, it means there's one left. Okay? Well, if you think about it, that makes sense too, because if I give you an array with only one element, that's how they got started, right? B is 0 and E is 0 to begin with. And that one single element that I have in that small, tiny little array can be the value that I'm looking for. So when B equals E, it is still okay. Okay, we have one element left to compare. So what do you think will happen when that element does not equal to the key? Okay, B and E are exactly at the same place. Depending on the comparison, I would either move B down here, or I would move E up here. Is that making any sense? Because for each iteration, one of them has to be adjusted. But when they cross over, what does it mean? If the index of the first element that may contain the value key is greater than the index of the element that may contain the value key, the last element, what does it mean?
You eliminated all the elements.
There's nothing left, right? That means there's nothing left. So the condition that we are looking for in order to indicate all elements are eliminated is just B is greater than E. As long as B is less than or equal to E, we're still okay, because the beginning is still not after the end. They can be the same place, okay? When they're exactly the same, that means we have one element left. But when the beginning is after the end, then we know there's nothing left.
The beginning is empty.
Yep, right? It doesn't make sense.
Right.
And that's why it signifies that we have made the conclusion that there's nothing, no element in the array may contain the value key. Okay. Yep. Go ahead.
I'm just curious, what would happen if all of the elements were identical?
Then it will find the first. Okay. In that case, there are.
Binary search, it would find the middle one, right?
It will look at the middle one first, and then based on that comparison, okay. So let me get this straight. You have the entire array having exactly the same value. Is that the value that you're looking for or not? Because if it is the value that you're looking for, hey, the first comparison will succeed and say, hey, we found it, no problem. So it only gets interesting when it is not the value that you're looking for, right? What would happen is one of B and E will go to the other extreme and go one beyond, depending on whether the only value in the array is greater than or less than the value that you're looking for.
What do you mean it would go one beyond?
Okay, well, let's take a look at the example here. So let's say the entire array has the value 3, okay? And you're looking for 4. So the first one we compare to is this one here. Okay, 4 is greater than 3. So we'll erase this part. And then of the remaining 2, we'll pick one to compare to. It doesn't even matter which one you pick. Let's say we pick this one. Now we eliminate this part here. We have one left here. We eliminate all of this stuff here. So E all this time is pointing here. What we are moving is B, because B initially is over here, then it is over here, pointing to the second one, and now it's going to be pointing here, and then after that it will point to the one below, which does not exist.
Okay, that makes sense.
But if you make this value 5, then E would move all the way and eventually become -1. But you come to the same conclusion that B is greater than E eventually. All right. So we only have one question left to finish up this algorithm, which is what kind of a loop are we looking at? Okay. At this point, we just know that it is some kind of a loop, but we have 2 kinds of loops to choose from. One is a pre-checking loop where we check the condition first, and then we, determine whether we want to go for another iteration or not. We have a post-checking loop, which means we perform at least one iteration, and then we decide whether we want to go back and perform another iteration. So in this case, the indicator would be the use of M here. Okay. You look at the condition of the loop, it depends on M, right? But when does M get its value the first time? Does it get its value the first time before the loop or during the loop? During the loop. So that means we have to perform at least one iteration for M to be meaningful. And that points you to which direction, pre-checking loop or post-checking loop? Post-checking loop, okay? Because you need one iteration to make M meaningful. So that means we can now finish up this entire thing and basically turn this loop, which is not specific, into something that is specific, which is repeat until. And that's the correct algorithm. So are there any questions about the binary search algorithm? Yep, go ahead.
Don't you need to specify that's a floor function?
The floor function? Yep.
Don't you need to specify that it is floor? So
Yep.
that actually makes it.
Right, so right here, what if, B plus E divided by 2 is a non-integer, right? What if it is something and a half, okay? Yep, so you have to pick one or the other number, okay? I'll give you an example here. What if B is 0 and E is 5, okay? Then M gets, 0 plus 5 divided by 2, which is 2.5. But 2.5 is not a valid index, okay? It is not an integer. So in that case, there's really no correct answer, because in this case, you can use a variety of functions and it will still work correctly. For instance, you can use the for function, which is what I use in my notes. Okay? The for function means, we'll take the largest integer that is less than or equal to 2.5. In this case, it is just 2, right? We can also use the ceiling function. The ceiling function looks like this. It is the least integer that is greater than or equal to the number that we are dealing with, which in this case would be 3. You can use the usual function called round, which means if it is greater than or equal to the half, you round up. For everything else, you round down. That works too. You can also use the function that only takes the integral part of a number, and that works as well. In other words, when you have 6 elements, so you have 1, 2, 3, 4, 5, 6 elements, there are 2 middle elements, and they're equally eligible as quote-unquote the middle element. You can pick this one as your middle element. You can also pick this one as a middle element. And either way, it works just fine. Okay, your binary search will retain its time complexity regardless of which one you pick. You can even have an algorithm to randomize this thing, right? Sometimes it picks the first one, and other times it picks the second one. And binary search will still work fine, no problem. It's just that for consistency, we just use one or the other, and the for function is just one of the many choices that we could use.
you said for consistency, is that consistency for you as a programmer?
No, just
Or
consistency as
consistency-
far as the behavior of the algorithm is concerned. So it is
Okay.
reproducible. If there's a bug, it's going to crash at the same time. It's going to give you the same wrong answer, all the time. Because if you randomize it, it's going to be a little bit harder to predict how it's going to crash the next time. Right? But in this case, we can use floor, we can use ceiling, we can use the usual round, and we can also use just the integer, take the integer part. Because for all non-negative integers, this is the same as just taking the integer part.
Am I understanding you correct that there's no advantage to either one?
There's no particular advantage to either one. Yep.
When you say just taking the integer part, is that like the mod function that we talked about before, or is that the
No, it's just taking the integer, like when you have 2.5, you drop the fractional part. You're basically just dropping the fractional part. So we can pick either one. The floor function is just one of the many things that we can choose. So there we have floor. All right. So let's go ahead and trace this a few times, and then we'll move on to subroutines. All right. So let's go ahead and paste all this stuff in. And we'll do a little trace. Well, we'll do a few traces. We'll do maybe 3 traces or so. Oh, you know what? I know what I should do. I'm going to plagiarize myself.
Is there a way to produce that?
And make this, as confusing as it possibly can.
Thanks.
But only to certain people, so it's not going to be. Okay, this is what I'll do. All right, I'm going to make this as confusing as it can get, kind of, in a way, because I'm going to use exactly the same test cases as in your homework assignment. And, oh, I forgot to open up another window first. Okay, so here's another window, and here's my trace. That's a screamer. All right, so there we have it. We have algorithm on one side, a trace on the other side, which is the same test case that you have to deal with in your homework assignment. Okay, so we'll go ahead and start with line 1. Line 1 is easy. B gets a value of 0. And for those of you who say this is really ugly, yeah, we can, just replace all that stuff with the actual arrow.
Close enough.
I think I can use the global search and replace to do this. There we go. All right. All right. So here's line 1, and line 2 is going to initialize E to bar A bar minus 1. Bar A bar in this case is 4. 4 minus 1 is 3. We do not trace line 3 because line 3 is just a marker, a bookmark that indicates the beginning of a post-checking loop. So we don't track those lines. We will start with line 4. Line 4 is updating M. It is the floor of B plus E divided by 2. In this case, B plus E is 3. 3 divided by 2 is 1.5. The floor of 1.5 is 1. Very good. And then we move on to line 5. Line 5 has to perform a comparison. A bracket M is less than K. Okay, we instead of K we have key. Okay, it's slightly different, but close enough. So A bracket M is A bracket 1, which has a value of 6. 6 is less than 8 is true. Okay. What? It is true. Okay, 6 is less than 8 is true. And then we go to line 6. Line 6 is going to change B. It is m plus 1. M is 1 already. M plus 1 is 2. So we are updating the value of B to 2. And then we move on to line.
Oh, we put it on column.
Sorry?
You put
Go to line 4.
Say-
on line 4.
On line 4.
Or never, 'cause-
Yep.
When you go to line 10 after 6, so that you could check and then go back.
Yep. So after line 6, we go to line 10. Okay, because line 6 is the end of one of the branches already, so we get out of the multi-branch conditional statement. We get to line 10. Line 10 has a longer condition to evaluate. A bracket m equals key is false. Okay, that is false. So we have to evaluate the other side of the disjunction, because one side being false doesn't mean the whole thing is going to be false. So we have to evaluate the other side, which is B is greater than E. B is greater than E is false too, because B has a value of 2, E has a value of 3. 2 is greater than 3 is false. False or false is false. So we don't have the exit condition being true. We have to go back to line 4 again. So this time on line 4, we are re-evaluating the floor of B plus E divided by 2. This time B has a value of 2, E has a value of 3. 2 plus 3 is 5. 5 divided by 2 is 2.5. Yep. Okay. So 5 divided by 2 is 2.5, and the floor of 2.5 is 2. Yep. So we'll go ahead and trace that. So m now gets a value of 2. We move on to line 5. And on line 5, we evaluate the comparison. A bracket m is A bracket 2. A bracket 2 has a value of 8. Okay, very good. So 8 is less than 8 is false. And we move on to line 7, because it's a multi-branch conditional statement. A bracket m, which is 8, is greater than k, which is also 8, is also false. And then we have nothing to do, because the conditional statement, the multi-branch conditional statement, doesn't have one case for A bracket m equals key, because when they are the same, we don't have to do anything. The exit condition will catch it. Question?
No, that you.
Okay. Yeah, the exit condition will catch it, because on line 10, the first thing the conditional statement, the condition checks is whether A bracket m equals k, and it is true already. And because we use short-circuited evaluation, we don't bother to evaluate the or B is greater than E part, because the first condition is true, and this is a disjunction. That is already enough reason for me to know that the entire disjunction is going to be true, and therefore we can now exit and say we're done. So are there any questions about this particular trace? Yep.
As far as the last check on 10, and the short-circuited part of it, if B was greater than E, do we just write that B greater than E because
No.
it's true?
No, you always evaluate from left to right. So you always have to evaluate A bracket m equals key first. If that fails, then you evaluate B is greater than E. Okay, because it's important to always use that order, because it is a part of the C++ language specification that for conditional statement, for disjunctions and conjunctions, they're always evaluated from left to right. Yep.
I know sometimes you don't care what we put in the comments if we add extra stuff, but in this case, if we read it from left to right, wrote that first, but we also wrote the other side of the or, would that, are you gonna mark that as wrong? Or ignore the short-circuit path?
In the homework assignment, I did not say that you have to indicate the use of short-circuited evaluation, so I will not take points off because of that. But in an exam, if the instruction of the exam is to demonstrate the use of short-circuited evaluation, then you have to do it the way that I'm doing here, which is only to evaluate as far as you need to find out what the answer is. Okay, that's a good question. Right, so that's the first one, and now we move on to the second test case. The second test case, is also coming from your homework assignment. I don't think it is confusing to most people, except for people who are looking for shortcuts. and say, I would just copy and paste text solution in class to my homework because they seem to be the same thing. All right, so we'll start with line 1 again. Okay, line 1, B gets a value of 0, line 2, E gets a value of 3, and then on line 4, M gets a value of 1, same as the previous one. And then on line 5, this time is a little bit different, isn't it? Okay, A bracket M is less than key is false because M is 1, A bracket M has a value of 6, K also has a value of 6, 6 is less than 6 is false. Then we move on to line 7. A bracket M is greater than key is false too because K or key has a value of 6. A bracket M, which is A bracket 1, also has a value of 6. 6 is greater than 6 is false. We got nothing else to do in the conditional statement, so we exit the conditional statement. We get to the end of the post-checking loop on line 10. And once again, we evaluate A bracket M equals key first, and it is true already, so that's why we don't bother to evaluate the right-hand side of the disjunction, and then we can exit the loop. Okay, it's pretty easy. But trust me, your homework is not going to be as easy. All right, so here's the last one. Okay, this one is the last test case of your homework assignment. And we'll go ahead and paste it here. This is our precondition. Line 1, same thing. B gets 0. Line 2. E gets a value of 3, line 4, M gets a value of 1. So, I'm not explaining that part because it's the same as the first test case. On line 5, we evaluate the condition. A bracket M is less than key. So A bracket M, which has a value of 6 because it's A bracket 1, is less than key, which has a value of 10, is true. Right?
Right.
Then we move on to line 6. Line 6 is going to update B to become M plus 1. M has a value of 1 at this point. 1 plus 1 is 2. Then we get out of the multi-branch conditional statement onto line 10. A bracket M is A bracket 1. It has a value of 6. 6 equals to key, which has a value of 10, is false. Okay, now you don't have to say it is false because it is just implied it is false. Then you have to evaluate the other side. The other side is B is greater than E, which is also false because B has a value of 2 and E has a value of 3. So B is greater than E is also false. We have false or false, which is false. So now we move on to the beginning of the loop again, which is on line 4, and recompute B plus E divided by 2 and then the floor of that. B is 2, E is 3, 2 plus 3 is 5, 5 divided by 2 is 2.5. The floor of 2.5, we have done that already, is 2. So now M gets a value of 2. We move on to line 5. We evaluate A bracket M is less than key. A bracket M is now A bracket 2, which has a value of 8. 8 is less than 10 is true. Okay, we move on to line 6. Line 6 wants to update it wants to update B, so it becomes M plus 1. M is 2 already, M plus 1 is 3, so now B gets a value of 3. Are we still doing okay so far? Okay. Now we move on to line 10. This is where B and E are exactly the same. Okay. We still have to evaluate A bracket M equals key first, which is false. And then we have to evaluate the second side, which is B is greater than E. 3 is greater than 3 is false. So now we have false or false, which is the entire thing is false. So that's why we have one more iteration to go in this case. Going back to line 4. Going back to line 4, B is 3, E is 3, 3 plus 3 is 6, 6 divided by 2 is 3, and the floor of 3 is just 3. So M gets a value of 3 in this case. We move on to line 5. A bracket M is less than key is false because A bracket M is A bracket 3. It has a value of 11. Key has a value of 10. 11 is less than 10 is false. We move on to line 7. A bracket M, which is 11, is greater than key, which is 10, is true. So this time we update E instead. So on line 8, we update E to m minus 1. M is 3, m minus 1 is 2. Then we proceed on to line 10. A bracket m equals key is false, because m at this point is 3, which a bracket m is a bracket 3 has a value of 11. 11 equals 10 is false. B, on the other hand, is 3. E is 2. 3 is greater than 2 is true. And if one side, at least one side of a disjunction is true, the whole thing is true. So in this case, it is true, and we get out of the loop. And we're done. So are there any questions about the binary search algorithm when it is correct? Okay, so in your homework assignment, you have to kind of pay attention because it's not the correct one. But I want you to see, what happens when the binary search algorithm is incorrect. And I'm only missing some little detail, right? The +1 and the -1, that's all that I was missing. And yet it can change the algorithm, in a very important way. All right, so that's binary search, and we are now done with the discussion of arrays. Well, not really quite so, because we'll use arrays, in subroutines and stuff like that too. But for the time being, our focus is no longer on arrays. Okay. All right. So back to the notes, back to the website. I want to show you where we are at this point. I'm going to turn editing on so I can highlight the section that we are on at this point. We are now moving on from topic 6 on to topic 7. So topic 7 is now getting the highlight because it is about subroutines. So we'll go ahead and start with topic 7. And you can start reading in this order, but I would also suggest reading updated subroutine notes first, because that's actually the updated version. The other notes is still correct. Okay, it's not conflicting with the updated version, but the updated version has a different presentation. To some people it's more clear. So I would use. That's why I still have links to both. Okay, because the first one is still okay, but the second one has a better presentation. Okay. Now subroutines is a really brand spanking new topic, and it's really important too. I'm going to start a new spreadsheet to illustrate what it means when we have subroutines. In the past, I tried to explain the necessity of subroutines before presenting the material, but I find it really difficult to do so, because I'm now switching the order. I'm explaining the mechanism first, and then we'll go back and talk about why it is important. Okay? Because in this class, we don't really write programs long and large and complicated enough that subroutines will make a huge difference. In your other classes, on the other hand, you will probably experience that part. Okay, so what I'll do is I'm going to give you an example of an algorithm that has a subroutine. So in this case, we'll define sub. I'll start with something simple. Okay, so this is just sub1. Okay, that's the name of the subroutine. Inside the subroutine, we can do whatever we want to do that we can normally do, and we have an end to the definition. So let's go ahead and use the indentation. All right. Yep.
Is a subroutine kind of similar to a module?
Not quite. It is the same as a function. Okay.
Yeah.
There are other names of a subroutine. It's also called a function, a procedure. Function and procedure.
Method.
Method. A method is kind of specialized because it only appears in classes. But yes, it is based on the same concept, except the scope is different. So all of those terms kind of refer to the same thing. Subroutine.
No, I was just thinking, it's like you have a go-to statement and then it goes back to.
It's like that, except the going to part is easy to figure out, but it's the coming back part that is a little bit tricky, right? Okay, so we'll go ahead and talk about this. So in this case, we'll have x initialized to 10, and then we invoke sub1, okay, we are actually going to call the subroutine. So the word that I use here is invoke, but in most other classes it's called, just call, C-A-L-L, call a subroutine, which is to trigger the execution of a subroutine. We'll explain exactly what that means, in just a little bit, okay. And then we'll come back to another statement called, which is just doubling the value of x. And then we'll find out what this is going to do. Most of you already know what it's going to do, right? I mean, just looking at the code here, you probably know just by the context that x will end up with a certain value. Okay, I'm not going to tell you what value it's going to end up as, but most of you probably have a good idea of what it is supposed to be. So we'll go ahead and trace it first, and then as I trace it, I'll explain what a subroutine is and how it is used. Now we have trace. We don't even need a comments column in this case. There are no conditions to evaluate. We can start with line number and x, which is my variable in this case. The precondition is I don't know anything about x, and then we can start tracing the program. The first thing we notice when we have subroutines in an algorithm is we don't start with line 1 necessarily anymore. When you have the definition of subroutines, you start with the first line in the algorithm that is not inside the definition of a subroutine. In this case, line 1 to 3 is a definition of a subroutine. So we don't start with line 1 anymore. We start with line 4. Okay, line 4 is the first line outside of the definition of a subroutine. Okay. In other words, a definition of a subroutine is kind of like an entry in a dictionary. Okay, it explains what sub1 is, but we don't necessarily need to refer to the word until when you're reading, an essay, you encounter a word, then you look it up, right? Okay, because there are thousands, tens of thousands, hundreds of thousands of entries in a dictionary. We don't really need to know the definition of all those words until we encounter those words when we are reading an essay. It's the same thing here. The definition of a subroutine simply means, sub1 means to increment x. But we don't need to refer to it until we have an invoke statement that basically says, okay, let's do it. Okay, so we're not going to do it until the invoke statement. Now, sometimes it is possible that you have subroutines that are defined and then not invoked at all. Okay, it is okay. Okay, it's perfectly fine. I mean, the dictionary has hundreds of thousands of words. Do you have to use every single word in an essay? No, it's not possible. Same thing here. Okay, so we'll go ahead and start with line 4. Line 4 is our good usual assignment statement. X becomes 10. Then we go to line 5. Now here is the fun part. Just by the word of call, invoke, or just the mentioning of the name sub1, and then we have sub1 on line 1, most people can make that association and say, oh, that means we have to continue execution on line 1, or more precisely line 2. So that part is absolutely right. Okay, so let's just forget about everything else and just say, yep, we know where to go now. We continue execution onto line 2, because line 1 is really not doing anything. It's just marking the beginning of a subroutine definition, so we don't really trace that line. The question now is, after line 2, what do we do? We are at the end of the definition of a subroutine. What do we do now? We continue execution onto line 6. Very good. But how did you know that you have to continue execution on line 6? It is the correct behavior, but how did you know that?
Because it's after invoking the...
Okay, it's right after the invoke statement. Very good. That's really... Okay, so line 2 is incrementing, so x gets incremented. And then on line 6, we double that, so x becomes 22. And then we get to post. So this is actually the correct sequence of the execution of the statements. But it doesn't explain what is happening so that we can continue execution on line 6 after line 2. Okay? It's kind of like when you're reading an essay, you encounter a word that you don't understand. You look up a dictionary, right? Okay, you look up dictionary, and it explains what the word means. So you comprehend, you get the word, the meaning of the word, and then you go back to your essay and continue reading after the word that you have just looked up in the dictionary. It's basically the same thing. But the question is, how did we know that after line 2 we are supposed to go back to line 6? So what I'm now going to do is to introduce some additional stuff to this trace that will explain how we can keep track of all of that stuff. Okay, so this is really the important part of this discussion is, but how did we keep track of all of that stuff? Okay, so at line 5, there are actually some additional operations that I have kind of neglected to mention. On line 5, the first thing it does when you invoke a subroutine, the very first thing it does is not to continue execution to the subroutine that has the name that you mentioned in the invoke statement. The first thing it does is to allocate a new column. This is something that we haven't done before. Okay, up to this point in this class, we only pre-allocate a certain number of columns to represent variables, arrays, and stuff like that, right? This is the first time that we say, you know what? I might want to allocate and make use of a new column occasionally. And this is where we will start to do it. So on line 5, the first thing it does is to allocate, and I'll say it probably many times in this class, we'll allocate the leftmost available column. Column B is used. Okay, column B is being used by variable X. We cannot reuse that one. But column C is the leftmost available column at this point. So we're going to allocate it and say, hey, column C, I need you to do something for me. Okay, I'm going to use column C to remember the return line number. Okay, RETLINE number pound is basically return line number. Okay, the return line number column does one thing, which is what you guys have done already mentally. It keeps track of, oh, which line am I supposed to go back to? What do you think? 6. Line 6, right? Because line 5 is invoked, so when the subroutine is done, we should continue execution on line 6, but not line 5, because if you come back to line 5, it will never end, right? It keeps invoking the same thing over and over again. So the return line number is line 6. Now, what I've also missed here is line 3 actually needs to be tracked. Line 3, if you look at line 3, it doesn't look like it's going to do anything, right? It's not like in an until statement where you have a condition to evaluate. It's just saying end define sub or end define subroutine. It's the end of a subroutine definition. But it actually got stuff to do. Okay? What it needs to do is to figure out where am I going to continue execution. That's its job. So on line 3, we actually have, once again, 2 things to do. The first thing is, sorry?
I was just going to say reference ret line.
Yep.
As far as word or return back to.
It has to look up now. Okay. I'm going to say this probably multiple times today. It's going to look up the rightmost return line number that is still existing. Okay? That is still existing. And in this case, well, we only have one column that has return line number in it, right? Which is column C. So it's going to look up that column and say, where am I supposed to go back to? Well, it tells me I'm supposed to go back to line 6. So right at that time, the first thing it does is to copy this line number to here. Okay, because it's just knowing, okay, we have to continue execution on line 6. And then the second thing it has to do is to say, oh, guess what? I don't really need that column anymore, so it is time to deallocate a column. In other words, I'm saying, column C, you're now free again. Okay, I'm no longer using you for anything.
That's
okay?
only X's?
Sorry?
That's only X's?
That's only... Okay, so the way I denote that is to copy and paste return line number, and then I use your format cell and use a strike through representation to indicate that this column is now from here, from this point and on, is no longer in use. So I can reuse a column. It's back to the recycle bin.
Reuse C.
Yes, I can. The next time, if I need another column, I will start with C again because it's now deallocated. Okay. So this is the full trace. Okay. Once we have subroutines, this is the full trace. And then people will say, but why do we need to go through all this trouble when we just need to say we have to go back to line
What
6?
if you have multiple subroutines or subroutines within subroutines?
Right? When the invocation is at one point of the trace, and then the return or the end of the subroutine is all the way down there, can you still remember where you're supposed to go back to? No, not so easy anymore. There was a hand. Yep.
Do we have to put a line number between the 5 and the 2?
Between the 5 and the 2.
Yeah.
No, you do not, because there are 2 things to do on line 5. Actually, there are 2 things to do on line 5. The first one is to allocate and then give it a value. I want to label column C so that I know what I'm using it for. Okay, so that's why it's taking up two rows in the trace. The second thing when you invoke is to just continue execution in the subroutine that you're invoking. So the 2 things you have to do is to, one, remember where you're supposed to return to, and then you continue execution. I cannot remember. I think. Okay. All right, go ahead.
Can you put it down as return line number and then sub 1, so that you remember that you're going?
No, we don't use. Oh, you mean on next to return line number?
Yes.
No, it doesn't matter. You can never return from the wrong place if you track everything correctly. This is all that you need. If you want to clarify, you can say return line number of sub 1, but trust me, it's not going to buy you anything.
Okay, as far as tracking, even like subroutines within subroutines and stuff like that.
Oh yeah. Before long, we'll be doing recursion, and we'll still be able to handle it. Yep,
Okay.
Go ahead.
And you have the subroutines within subroutines. Do you move them over to D, or do you just keep listing number after number?
We move on to D and E and so on. And it can even be the same subroutine in recursion. So this is going to get very interesting, even though the mechanism itself is really simple. In the cases of recursion and whatnot, the difficulty of recursion is not the concept itself. The difficulty of recursion is people overthink it. Okay, the mechanism is extremely simple, but when people overthink it, then problems happen. Yep, go ahead.
Is the return line number, is that an actual variable? Like, could you perform an operation on that?
It is not a variable in the sense that it is accessible to your code, not intentionally.
Right.
But sometimes you can trash it. Remember the discussion of arrays? What happens when you access an array out of bound? That is, sometimes what you can step on is quote unquote the return line number. Yep. Okay.
Well, in your programming, isn't it when your program actually executes, like after you've compiled it, that's actually an allocation of memory space, isn't it?
Yes, it is using up every column that we talk about, other than line number and comments. Okay, those 2 are really strictly for tracking purposes, and it doesn't really use up any space when the program is executing. But all of the other columns for our variables, return line number, and everything else that we will talk about in this class, they actually consume actual memory when your program executes. So the more columns we are using, the more memory we are actually using in the program. And that's why I talk about this in this particular fashion, so that when you guys move on to cisp300, which is assembly language programming, you will see basically the same thing again, but it's just called different things. Okay, but it's the same concept. So I'm basically prepping all of you to be ready for cisp300. Assembly language programming.
Through return line, so we can technically allow more memory available again.
Sorry, say again.
Is that why we would strike through or give a command to strike through?
The strike through means we are no longer using column C, so it is once again available.
So just for that little bit with the subroutine, we used a little bit of extra memory, and now
Right.
we're allowing it to be available again because we're removing that.
We are
column.
We are freeing that column, so it
We're
is now
deallocating.
available again. We're deallocating it. Okay, so let's go ahead and take a look at a second example. I think either today or on Thursday we'll get to recursion, which is a subroutine invoking itself. Okay, but before that, we'll go through a few more examples first. Okay, so once again we have defined sub. We'll call this sub 1 again. Okay. And it's going to do the same boring stuff as last time, just adding with x, and define sub, Okay, and we have the initialize x again. This time we'll start with 5. Okay, doesn't matter. And then we have invoke, sub1, and then we'll do something to it. So we'll get, say, x gets x times 3, and then we'll invoke sub1 again, and then we'll do something else to it. X gets x plus 5. Okay. So this time we have 2 invocations of sub1 in the algorithm. Okay, so we'll see what happens to the columns that we are tracking in this case. The only indentation is here. All right, so we'll go start a new window for the trace. All right, we got line number, we got x. It is unknown to begin with as our precondition. We start execution on line 4 because it is the first line outside of the definition of a subroutine. And on line 4, x gets initialized to 5. And then on line 5, we have our first invocation. 2 things it has to do. One is to allocate the leftmost available column. In this case, it is column C. And remember which line we are supposed to continue after the subroutine is done, which is on line 6. The second thing it has to do is to continue execution in the subroutine. In this case, it is sub1. We start execution on line 2. So is that okay so far? What an invoke statement is supposed to do? Yep.
Do we automatically skip to line 4 every time?
We skip to line 4? Yes, we automatically skip to the first line that is not inside a subroutine definition. All right. So now we continue on line 2. Line 2 by itself is really simple. Okay, all it's going to do is to add 1 to x. So x goes from 5 to 6. Then we get to line 3. Line 3 is the end of a subroutine. What it needs to do is to go back to where we're supposed to continue execution after the invoke statement. But it doesn't have to look very far because it has 2 things to do. One is to look up the rightmost active return line per column, which in this case is column C. Column C says, oh, we have to continue execution on line 6. Fine, we'll continue execution on line 6. Make a note of that. And then what it needs to do is to say, oh, okay, I have just used what is on column C. So column C is no longer useful to me. I'm going to deallocate it so that somebody else, if they need it, can use it again. And then we continue execution on line 6. Line 6 is just tripling the value of x. So it goes from 6 to 18. And then we move on to line 7. Then you will say, we know how to do it already. Well, that's good. I'm glad that you know how to do it already. So we have 2 things to do when we invoke a subroutine. Allocate the leftmost available column to remember which line you're supposed to go back to. Okay, so what are we going to do? Which column am I going to use?
C.
Column C, because column C is now free. It is available. I just deallocated it on row 7 of the trace. So now I'm reallocating column C, but I cannot put, I don't want to put a 6 here anymore, right? Because the continuation is on line 8. Very good. So we are now continuing on line 8, and that's the first thing we have to do when we are invoking a subroutine. The second thing is simple. We just continue execution in the subroutine itself, which in this case is line 2. It adds 1 to 18, becomes 19, and then we go to line 3. Once again, line 3 has 2 things to do. Look up the rightmost active return line number. Which column?
8.
Column C, it indicates 8, okay? So that means we have to continue execution on line 8 here. But once we make use of this value, it means this column is not useful to me anymore. So we'll basically just denote and say, okay, that column is now once again free, available to whoever wants to use it next. And then we continue execution on line 8 here. X gets x plus 5. So we go from 19 to 24, and we're done. We get the post. Yep.
So if you didn't end the return line on the first section and you were marking another return line spot that goes on to column D, you would have to change your all your stuff. But see what I'm saying? Like if you're trying to mark several of them, you go columns over until you
Well, in this program, you cannot do
Yeah,
that.
this one's different.
This one only has
Just
one
in
single subroutine definition. It
Yeah.
doesn't call itself.
Oh.
And then so everyone else can call it, but you cannot stack up,
Yeah.
invocations. But
Okay.
the next one,
Okay.
that's a good question. So you are already thinking ahead of me and say, but what if we have, tricky situations like that? Which is good. That's good. That is active participation. All right. So here we have another example. So we have define sub 1. Okay, we'll use the same boring stuff in sub 1. And then obviously we'll have a sub 2 this time. Define sub 2. And in sub 2 we're going to do something like this. We'll say, okay, let's make this not so confusing yet. Because I can switch the order to make it more confusing, but if I don't switch the order, it is actually a little bit better. Okay, so now we have sub 2 having an invocation of sub 1. And outside of the definition, we'll just go ahead and initialize x to, say, 3 this time. And then we'll go ahead and invoke sub 2 first. And nobody says that I cannot invoke sub 1 from outside. I mean, sure, we can do that. And that's the end. Okay, I don't have anything else to do after invoke sub 1, which makes a very interesting return line number. Not so interesting if you already know, the mechanism itself is really just saying, oh, okay, we apply the same concept, in this case. Okay, so now we have line number, we have variable x, unknown to begin with as our precondition, okay? Where do we start this time? It's not line 4 anymore. Yep, we start with line 8. It is the first line outside of the definition of a subroutine. So on line 8, x gets a value of 3. No big deal. We move on to line 9. It is invoking sub 2. So once again, the same boring 2 steps that we have to do for every invocation. Allocate the leftmost available column. Label it return line number. And write down where we are supposed to continue after the invocation. The invocation is on line 9. Do we have anything else to do after line 9? Yeah, we got a line 10 that got stuff to do. Okay, so we'll return to line 10 after sub 2 is done. Okay, and that's the first thing we do when we invoke a subroutine. The second thing we do in a subroutine invocation is to continue execution in the subroutine. So where am I supposed to go this time?
6.
5.
Line 5. Okay, line 5 is where I'm supposed to go, and I'm done with the invocation itself. Okay, are we doing okay at this point?
Yep.
Okay, so even though I'm invoking sub 2 instead of sub 1 this time, and it's starting at a different line, the mechanism is identical to what we had before. Except this time on line 5, I have another invocation. Oh no, what am I going to do here? Run around like a chicken without his head.
Because we have the allocated C, we have to use D at this point, the red line.
Exactly. In other words, nothing new here. Same boring 2 steps. Allocate the leftmost available column. Column D, right? Column C is now in use. I cannot use that column at this point, so I have to use column D as the leftmost available column. I cannot just randomly pick a column somewhere. It has to be the leftmost one. So now I label it, you know what? Same thing, return line number. And we have to continue on to line 6 because the invocation itself is on line 5. So now we have to continue on to line 6. That's the first step of invocation. Second step of the invocation is to continue in the subroutine that we are invoking. So where am I supposed to go this time? It's invoking sub 1, and sub 1 is, yep, on line 2. Line 2. Continue execution on line 2. Once I remember I have to continue on line 6, I continue on to line 2. Are we still doing okay? So before, okay, this is what it is. Okay, in other words, if this is a dungeon, if I'm exploring a dungeon, it's basically saying before I walk into a door, I leave a little note to say when I come back here,
Turn left.
Turn left. Exactly, because I came from the right hand side. Exactly. So that's exactly what I'm doing here.
You're establishing a small set of guidelines just prior to getting into something that may be a little more complicated. And
Yep. Except it's not a piece of breadcrumb, so I don't have to worry about somebody else eating it. And that's why I don't want to use the same column, because I don't want to use the same breadcrumb for everything, because then I'm going to lose track, right? So, very good. So on line 2, we do the same boring stuff. You know, we add 1 to x goes from 3 to 4, then we get on to line 3. Line 3, once again, at the end of a subroutine, we have to do 2 things. Look up the rightmost active return line number. Which one are we looking up this time?
C.
Column
D.
Column D, the rightmost. Remember, the rightmost, the most recent. Okay, so column D is our rightmost, the most recent return line number. We use that to help us determine where to go back to. Okay, so we look it up, we say, okay, we have to continue on to line 6, but as soon as we make use of that, we have to say, okay, we don't need that anymore, make it available to somebody else. So we'll go to right click, format cells, strike through. All right, so those are the 2 things we have to do at the end of a subroutine. Okay, look up where am I supposed to continue execution, and then deallocate a column that contains that very same information. In other words, as soon as we make use of the breadcrumb to tell us to make a left turn, we pick it up and
No, you don't eat it. When you're talking, you're already using it.
yeah, we put it in a recycle bag.
Because you're hungry.
Okay, so now that we are on line 6 is pretty easy. We're just adding 2 to x. X goes from 4 to 6, and then we get onto line 7. Line 7 is the same boring stuff, right? Same boring 2 steps. Look up the rightmost active return line number. It's column C, because the column D is no longer active. It is used up already. It is deallocated. It's a thing of the past. So now column C becomes our rightmost active return line number. Yep.
At this point, your program wouldn't even know that D even existed, would it?
That's an interesting question. You no longer know what column D has. Okay, as far as memory is concerned, you cannot destroy it. You just don't. It's okay.
It's available but has no value.
It has a value that you cannot predict. Okay. In other words, you know, once we deallocate column D, there can be other things that you are not aware of making use of column D. In other words, you cannot count on column D still having a return line number of 6 anymore. Once you deallocate it, you're basically telling the system and say, okay, column D is now available, and the system can do whatever it wants to column D. Possibly nothing, but possibly something else. Okay, but whatever you have still allocated is still yours, and you can count on column C still has a value of return line number 10 at this point.
Right.
Okay, so the whole point of allocating and deallocating is really moving a boundary of what is yours and what is not. And what is not yours is still there, it still exists. It's just that the value in those columns may not be what you think it is anymore. Okay, so now that we're on to line 7, we have to do the same boring stuff. You know, look up the rightmost return line number that is still active, which is column C. Column C tells me I have to continue execution on line 10, so we say that. And then the second thing we have to do is to remember to deallocate it, so that column C is now deallocated, and then we continue execution on line 10. Line 10 says invoke sub 1. I mean, I'm hoping that this is getting boring.
Yeah, you're there.
That's good. Boring is a good indicator in this case. As long as it is because you know what it is going to do, and tech is going to say the same boring stuff again, because I am. So on line 10 is an invocation. We do the same boring 2 steps. We allocate the leftmost available column. Which one is our leftmost available column?
C.
Column C. All right. So we reallocate column C right away and say, okay, I need to remember where I'm supposed to go. Oh, this is different. Where am I supposed to go after line 10?
Post.
Okay. Then you just say post. No big deal. Okay. Post is basically just an imaginary line number that is at the end of the entire algorithm. That's basically all that it is. Okay, and that's the first step. Second step is to continue execution in the subroutine that we're invoking. In this case, it's sub1, so we continue on to line 2. Line 2 is adding 1 to x. X goes from 6 to 7. We go back to line 3. We look up the rightmost active return line number, and that would be column C. Okay, so we say, oh, it's telling me to continue execution at post, and now we no longer have any use of that column, and then we continue at post. Hey, we're done. Finish line. Yep.
In some programming languages, or at least the one that I wrote with a little bit of Python there, you can like call math functions. Are those all subroutines, or is that different? Is that something different?
It depends. I mean, there are sometimes subroutines can incur overhead. So in a compiled programming language like C++, certain things are just done in place. Okay, they just do it right there instead of invoking a subroutine. Because you can see that a subroutine always has the overhead of allocating a column and deallocating a column. So that's basically overhead. Sometimes it depends on the language. What is actually a subroutine, and sometimes what is not a subroutine is. It's just done in place. Yep.
Wouldn't floor be an example of a subroutine? Just an internal one?
Can be. It can be a subroutine, but it doesn't. The floor function.
Yeah.
But the floor function is different from a regular subroutine like this one because it has a return value. Okay, we'll talk about subroutines that have return values later on. Okay, now we still have 4 minutes. Okay, so with 4 minutes, what I can do is I can give you a brain teaser. I know how much you guys like brain teasers, and it is the preparation for the next class. Okay, so the brain teaser looks like this. Okay, we have define sub, and once again we'll call it sub1. But this time sub1 is a little bit more complicated than the previous one. It just says if x is less than 3, then x gets x plus 1. Invoke sub1, and if, and define sub. And if I adjust the indentation, you guys will see a little bit better what it is going to do. Maybe. And then this time I guess say x gets initialized to 0. Invoke sub1. And that's your brain teaser. Okay, the brain teaser is to figure out what this algorithm is going to do.
It's like just off the top.
It looks like it's going to spin like that, but in reality, it's going to spin like. Okay. So it's almost like a wind-up toy. Okay, you wind it up 3 times. Exactly 3 because of the comparison in the conditional statement. You let go and it will unwind exactly 3 times. Yep.
Is that assuming that you don't have negative, x doesn't have negative?
X can start with a negative value, but eventually, if you keep adding stuff to something that was negative, eventually it will get to 3. So it's not infinite for sure. If x is greater than or equal to 3 already, it doesn't even go through the inside or line 4, so you don't have a problem. So this is your first encounter with a recursive subroutine, okay? And typically that is reserved to a much later class, but I think we can do it now, okay? The trick to this brain teaser is simple. Don't overthink it, okay? Do all the things, the mechanisms that we have talked about in today's class exactly the same way, and it will work just fine. All right, I'll see you guys on Thursday. Thank you.
It says exam 1 next to my name. What does that mean?
Did you miss exam 1?
No, you handed it back to me.
I did. Okay,
Yeah.
I did not have your score. Did you check your grades in Noodle?
No, I did not.
Okay, you might need to give it back to me because for whatever reason I skipped yours.
F. Second, right on it.
Hmm?
F on it.
Yeah. Well, it's not an F. It's just